In this video, we will explain in general about neutronic analysis in nuclear reactors. This is the diagram of chain fission reaction. As we know, nuclear energy is released through a chain fission reaction where neutron from a fissile nuclear trigger fission in other fissile nuclei, continuing the process. In the neutronic analysis of nuclear reactor core, the main aspect that must be carried out is to create an analytical and quantitative physical description of the state of the neutron in the reactor core. Next, we will discuss the neutronic aspect of nuclear reactors. The first is about neutron transport and diffusion equation. A neutronic analysis in nuclear reactor involves describing the physical properties of the neutron state in the reactor core. This description includes neutron population, neutron distribution, neutron energy, neutron density, neutron flux, and more. One of the theories addressing this aspect is the neutron transport equation. The neutron transport equation can be written as in the equation 1. You can see in equation 1 with V is neutron velocity, omega is neutron direction, sigma t is total macroscopic cross-section, pi is neutron angular flux, and S is source density function. The transport equation is relatively challenging to solve. Therefore, several simplifications can be made, such as the diffusion approximation. The diffusion equation is obtained by integrating its term in the transport equation over the solid angle. The diffusion equation can be written in the equation 2. You can see equation 2 represents the neutron continuity equation. The subsequent simplification involve assuming that all neutrons have the same speed or same energy. The neutron source is isotropic and the scattering interaction are isotropic. Thus, equation 2 will become equation 3 with D is neutron diffusion coefficient, sigma A is macroscopic absorption cross-section. Equation 3 is one speed or single group neutron diffusion equation, which is quite useful for understanding the basic concept of nuclear reactor core neutronic analysis. However, for more accurate analysis, this equation is insufficient, and multi-group diffusion equation is required. To derive the multi-group diffusion equation, the concept of neutron balance can be utilized as equation 4. You can see this is about the rate of change in the number of neutrons in group G. Based on equation 4, you can see there are two factors that increase the number of neutrons in a group. The first is neutron appear. The first is neutron appear in a group G from neutron source. These neutron sources are mainly nuclear fission reaction. The second is a neutron with any energy undergo a nuclear scattering reaction, so that their energy changes and is included in the G group energy interval. You can see also there are three factors that reduce the number of neutrons in a group. The first is neutron leaks, neutron coming out of the reactor core. The second is absorption. Neutrons are absorbed by the material in the reactor core. And the third is the neutron in group G undergo a nuclear scattering reaction. So their energy changes and leave the energy interval of group G. Based on the diffusion approximation, the mathematical expression of the neutron balance equation in equation 4, we can write on equation 5 with scattered out cross-section in equation 6 and with source term in equation 7. If equation 5 is rearranged, it will take the equation 8 with kg is the probability of the occurrence of a neutron resulting from a fission reaction with group energy G. Sigma F is a macroscopic cross-section of fission reaction. And another symbol like Kf. Kf is effective multiplication factor. We will discuss about this in the next leg, in the next slide. This is about multiplication factor and reactivity. Chain reaction are quantified by the multiplication factor, or K, defined as the ratio of fission or fission neutron in one generation to those in the previous generation. We can see in equation 9, K is the number of neutron in a generation divided by number of neutron in the previous generation. Another key parameter in reactor cores is reactivity, or rho, which is closely related to the reactor control system. Reactivity is defined as equation 10. Rho is K minus 1 divided by K. In the reactor, the chain reaction is controlled by adjusting the multiplication factor, or K, or reactivity. To increase power, K is set above 1, or rho is set above 0. When desired power level is achieved, K is maintained at 1 and rho at 0. To reduce the power or shut down the reactor, K is set below 1, or rho is set below 0. The multiplication factor, K, can be calculated using probability principles. If N1 is the number of neutron in the initial generation, the formula for the number of neutron in the next generation is N2 equal eta F PNL N1. You can see in equation 11. With F is thermal utilization, eta representing the number of fission neutron produced per neutron absorbed in the fuel, and PNL is non-leakage probability. The mathematical formulation of the multiplication factor become equation 12. Where is K equal N2 per N1. If no neutron escape the reactor core, the non-leakage probability equal 1. Thus, the infinite multiplication factor can be defined as K infinite equal eta F. You can see in equation 13. There are two types of non-leakage probabilities. One is the non-leakage probability for fast neutron, and the second is non-leakage probability for thermal neutron. The multiplication factor in a finite system can be determined by calculating the effective multiplication factor. You can see in equation 14. This K effective or effective multiplication factor is eta F non-leakage probability for fast neutron and non-leakage probability for thermal neutron. Next, we will discuss about burn-up analysis. During operation, reactor core undergoes depletion due to fission reaction and nuclear transmutation. These changes must be analyzed as the impact neutron parameter. In burn-up analysis, the burn-up equation is solved by determining the core density as a function of time and position, with neutron flux known beforehand. Burn-up analysis is carried out to determine the characteristic of isotopic changes in nuclear reactor. The reaction rate equation describes the nuclear number density. If Na is the density for type A nuclides, then the equation becomes equation 15. This is the burn-up equation, with the first term on the right side being radioactivity decay from A, the second term being neutron capture from A, the third term being decay from B to A, and the fourth term being the transfer from C to A via neutron capture. The burn-up equation for each material is in equation 16, where Ni is the atomic density of group I, lambda I is the decay constant, sigma AI is the microscopic absorption cross-section, and SMI is the production rate of nuclide I from nuclide M. In the neutronic calculation, the burn-up equation is typically solved alternately with the multigroup diffusion equation. After solving the diffusion equation, the neutron flux obtained from the multigroup diffusion result is used to carry out burn-up analysis. Then, changes in composition due to the burn-up equation will be included in the recalculation of diffusion constant, reaction cross-section, and the others. There are three methods for determining the analytical solution of burn-up equation. The first is explicit method, the second is implicit method, and the third is semi-implicit method. Before solving the burn-up equation, the first thing we must do is calculate the atomic density of each material used in reactor core. Density values based on atomic fraction can be calculated using the equation 17 with the concentration of the isotope given by the element fraction in equation 18. Okay, that's all our presentation. Thank you for your attention.